Hello, geometry students. Welcome to our 5.1 notes, bisectors of triangles. So the first thing I want you to look at is this diagram, and I have a question. What is the relationship between segment OC and segment HS? So here's OC and here's HS. Well, I see a right angle symbol, and I also see these tick marks. So that means that OC is the perpendicular bisector of segment HS. Perpendicular bisector. Okay, so suppose that you were to walk from O to C. So you start here and you start walking along this path from O to C. If you stopped at points A and B and C, how would your distance from home compare to your distance from school? So let's say we stopped at, so we start walking along, we stop here at point A. So let's compare the distance from home to point A and the distance from school to point A. And then let's continue walking and stop at point B. Let's compare the distance again from home to point B to compare that distance to the distance from school to point B. And then continue your walk along to C. And now let's compare the distance from H from home to point C and from school to home to point C. Well, my drawing isn't very good, but I think you can tell that in each case, every time you stop along that perpendicular bisector, your distance from home to school would be congruent to your distance from, your distance from home to that point on the perpendicular bisector would be the same as the distance from school to that point on the perpendicular bisector. So that demonstrates our first theorem called the perpendicular bisector theorem that says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, so in this case, everywhere we stopped along this perpendicular bisector, we were equidistant from each endpoint. One endpoint was at home and one endpoint was at school. So this is kind of a wordy theorem, so if we ever need to use it as a reason and a proof, let's write out how we could write it in shorthand. So we'll write it like this. If a point is on the perpendicular bisector of a segment, then we can conclude that it is equidistant from the endpoints of that segment. Okay, so that would be a shorter way to state that theorem if we ever need it as a reason and a proof. Okay, so now let's take a look at the converse situation. So here in this next picture, we have these little wires here. These wires that are used to stabilize trees or poles are called guy wires. And they're often used to help trees grow up straight. Now, if the two guy wires in the picture are congruent, so let's go ahead and mark them congruent. So if these two guy wires are congruent, then what do you think is the relationship between the tree and the ground? Well, this is just the converse of the perpendicular bisector theorem that said if a point was on a perpendicular bisector, it was equidistant from the endpoints. Well, here we have a point that is equidistant from the endpoints, so our conclusion can be that that point right here is on the perpendicular bisector of the segment. So the converse of the bisector theorem says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of that segment. So you can see over here on this diagram, look at point E. See these tick marks? That tells you that point E is equidistant from these two endpoints A and B. Therefore, we can conclude that E is on the perpendicular bisector of segment AB. So again, this is a wordy long theorem, so this is how we'll write that theorem in shorthand. We'll say if a point is equidistant from endpoints, okay, then we can conclude that it is on the perpendicular bisector of that segment. Okay, so that'll be a shorter way to write that converse of the bisector theorem. Let's continue now by learning some new vocabulary. And that is when three or more lines intersect, we say that those lines are concurrent. C-O-N-C-U-R-R-E-N-T. So when three or more lines intersect, they are called concurrent. Like in this picture, we have three lines that intersect at one point, and that point has a name. It is called the point of concurrency. So point of concurrency. Okay, so now let's use this vocabulary and see how it applies to triangles. So if we have the point of concurrency of the three perpendicular bisectors of a triangle, like in this picture, we can see that all three of these lines, each one of them is perpendicular to a side, and it also bisects the side. So if we have the three perpendicular bisectors of a triangle, they come together at a common point called the point of concurrency, and in this context, that point has a name. It is called the circumcenter. Okay, so the circumcenter is the point of concurrency of the three perpendicular bisectors of a triangle. Okay, and we have a circumcenter theorem which says the following. The perpendicular bisectors of a triangle intersect at a point called the circumcenter. The circumcenter. And that circumcenter is equidistant from the vertices of a triangle. Okay, so if you take a look at this picture, this segment, now don't look at the red segments, look at these blue segments. Oh, I'm sorry, I said that backwards. Don't look at the blue segments. I need you to look at the red segments. Each one of these red segments is a perpendicular bisector. The red segments come together and they form a point called the circumcenter. So now what I want to do, I'm going to highlight these three segments. These three segments that I'm highlighting in yellow, those indicate the distance from each vertex to the circumcenter. And what this circumcenter theorem is telling us is that that point of concurrency is equidistant from all three of those vertices. So let me just restate that. This point P, that is the point of concurrency of the three perpendicular bisectors, it's called the circumcenter, and that circumcenter is equidistant from the vertices of the triangle. So what this is saying, let's go ahead and write this in shorthand, is that if we have a point that is a circumcenter of a triangle, we can conclude that that circumcenter is equidistant from the vertices of the triangle. So let's talk about where the circumcenter gets its name. The circumcenter gets its name. Here's a picture of a circumcenter, which as you can see is the intersection. It's the point of concurrency of three perpendicular bisectors of a triangle. That point, that circumcenter, is also the center of a circle that is circumscribed about the triangle. Circumscribed about the triangle means that every vertex of the triangle lies on the circle. So that's why it's called the circumcenter. So the circumcenter gets its name from the fact that it is the center of the circle that is circumscribed about and we need to, there's a typo here that should say about a triangle. Sorry about that. Okay. The circumcenter can be on the inside, on the outside, or on the triangle, depending on what kind of a triangle we're talking about. So in this first picture, we have the three perpendicular bisectors. And let's go ahead and make some marks on here to indicate that this line is a perpendicular bisector. We need to mark that it is perpendicular to a side and it also bisects the side. Okay, and we could do that with all three segments. It's just that if we do the picture gets pretty messy. So even though it's not marked, every one of these dotted lines is a perpendicular bisector of a side of a triangle, and they meet at a point called the circumcenter. Well, for this triangle, let me just go ahead and let's see, draw the circle that would be circumscribed about that triangle. We can see how the circumcenter is the center of that circle. And for this triangle, which happens to be an acute triangle, Okay, acute triangle, that circumcenter will be in the center, okay? In this next picture, take a look at every one of these dotted lines is, again, it's a perpendicular bisector of a side of the, triangle, okay? So let's see, this is a perpendicular bisector. Once we mark all these, it gets a little messy, but I want you to be sure and see that every one of these dotted lines is a perpendicular bisector of a side of the triangle. You'll note that their point of concurrency is outside of the triangle. Let me just go ahead and see if I can draw the circle that would be circumscribed about this triangle, and you can see that this point of concurrency is the center of that circle. Well, what kind of a triangle is that? That is an obtuse triangle. And then last but not least, take a look at this picture. Again, every one of these dotted lines is a perpendicular bisector. I'll just mark a couple of them. It's a perpendicular bisector of a side of the triangle, and you'll note that their point of concurrency is a point that's on the circle. And again, let me just one more time draw that circle that's circumscribed about the triangle, and you can see how that point of concurrency, that circumcenter, is the center of that circle. So when the point of concurrency is on the triangle, that's when that happens when the triangle is a right triangle. Now we're going to take a look at a couple of more theorems, and to illustrate this first theorem, let's suppose that a baseball player is standing on this ray PQ, and PQ, you'll notice, happens to be the angle bisector of the angle that's formed by the baselines from home base to first and home base to third. So suppose that a player is standing right here at point Q that's on that angle bisector. Well, how do you suppose his distance compares the distance from first base to where the baseball player is standing and the distance from third base? Let's just go ahead and draw that in. So from first base to where the baseball player is standing and from third base to where the baseball player is standing, I think you can see from the picture that those distances are going to be the same. So if a baseball player is standing on PQ, which is an angle bisector, then how does his distance to the first base compare to his distance to third base? Well, they're going to be the same. So we can say that he would be equidistant from both of those bases. So that illustrates our next theorem called the angle bisector theorem, that says if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So let's write that out how we'll write it in shorthand. We'll say if a point is on an angle bisector, then that implies that the point is equidistant from the sides of the angle. Okay, if we ever need to use that theorem as a reason and a proof. So I want you to take a look at this diagram here. So here we have point F that is on the angle bisector of angle DBE. See, these arcs show that this ray is an angle bisector. So F is, according to this theorem, then F is going to be equidistant from the two sides. Notice why these right angle symbols are there. That's because, remember, the definition of the distance from a point to a line is the measure of a segment that's perpendicular to a line. So what this theorem tells us is that if F is on that angle bisector, then F is equidistant from the sides. And to illustrate this next theorem, let's take a look at this scenario. If point A is equidistant from the blades of the scissors, okay, so here's point A, and you'll see that we have these distances from A to each blade of the scissors marked because it is remember, the distance from the point to the blade is the measure of the segment that's perpendicular to that blade, and notice that they are marked congruent. So if A is equidistant from the blades of the scissors, then what is the relationship between the dotted line and the angle formed by the blades of the scissors? Well, I think what we can conclude is if A is equidistant from the blades of the scissors, then this dotted line would be the angle bisector of the blades. So let's just write that down. So the dotted line, I'll just say the dotted line is an angle bisector. All right, so that illustrates what this next theorem says. It's the converse of the angle bisector theorem, which says if a point in the interior of an angle is equidistant from the sides of an angle, then the point is on the bisector of the angle. On the bisector of the angle. So here's how we'll write that in shorthand. We'll say point equidistant from sides, that would be from the sides of an angle, implies that the point is on the angle bisector. Okay, that's how we'll say that in shorthand. So if you take a look at this picture, here we have F. Notice that we've got the distances marked from F to either side of the angle. Notice that those distances are marked congruent. So if those distances are congruent, meaning that F is equidistant from the sides of the angle, then we can conclude that F is on the angle bisector of the angle. Okay, so you might recall that we were just a few minutes ago talking about the three perpendicular bisectors of a triangle, and we talked about how those three perpendicular bisectors had a point of concurrency called the circumcenter. Well, the same thing is going to be true for the angle bisectors of a triangle. The angle bisectors of a triangle are going to be concurrent, and that point of concurrency has a name. It is called the incenter. You might recall a while back when we were doing a project, it was a project on constructions, and you actually constructed the incenter of a triangle. And the way you constructed that is you constructed the three angle bisectors of the triangle, and you found their point of concurrency. Well, now you know that that point has a name. It's called the incenter. Now, why is it called the incenter? It's called the incenter because its name comes from the fact that it is the center of the circle that is inscribed in the inside the triangle. So what that means is we're talking about the center of a circle that is inscribed in the triangle. It's inscribed in the triangle if the triangle is tangent to all three sides of the triangle. You might recall doing that in that constructions project. So now that you know what an incenter is, let's take a look at the incenter theorem. The incenter theorem says the angle bisectors of a triangle intersect at a point called the incenter that is equidistant from the sides of the triangle. So here's how we will write that in shorthand. We'll say incenter of a triangle implies that that point, the incenter, is equidistant from the sides. Okay, so if you'd like to take a look at this diagram, here we have all three angles have been bisected. Those three angles have a point of concurrency. Let me just highlight the angle bisectors. So here are three angle bisectors. Okay, they have a point of concurrency, and you can see from the diagram that that point of concurrency is equidistant from the sides of the triangle. Okay, now remember that circumcenter could be on the inside of a triangle, the outside of a triangle, or on the triangle. However, that's not going to be true with the incenter. The incenter will always be located in the interior of a triangle. It doesn't matter whether that triangle is acute, it doesn't matter whether that triangle is obtuse, or if it's a right triangle. Anytime we have an incenter, that incenter will be located in the interior. So just to demonstrate, make sure that you know that these are incenters. If we take a look at this ray, it is an angle bisector, so let's mark it. Okay. Likewise, this ray is an angle bisector, and the third ray is an angle bisector. So the dotted lines or the dotted rays are angle bisectors. They meet at a point called the incenter, and that incenter is the center of the circle circumscribed in the interior of the triangle, and it is also equidistant from the sides. And that will be true for all three cases. In all of these pictures, the dotted lines that you're looking at are angle bisectors, and They meet at a point called the incenter, and that incenter will always be the center of the circle inscribed in the circle, and that incenter will always be equidistant from the sides. Okay, so what I want to do right now is do a few of the homework problems with you, just so you have an idea of what you're doing. Now, the directions say work these on notebook paper. If you can squeeze it on this paper, that's certainly fine. But if you find you need more room, you might want to move to a piece of notebook paper. So let's take a look at number 9. The directions say find each measure. So what are we looking at here? Well, if you look at segment LN, we can see that LM is 10 and NM is 10. So that means that this segment is a bisector, and the right angle tells us that it's a perpendicular bisector, okay? So we have a point P that lies on the perpendicular bisector of a segment, and so our theorem said that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. So we can go ahead and set 2x minus 4 equal to x plus 5, and then I'll leave it up to you to solve for that. Conversely, let's take a look at number 12. Here, number 12, we see that point D is 6.5 units away from G, and D is 6.5 units away from E, so that means that D is equidistant from the endpoints of the segment. Therefore, we know that D lies on the perpendicular bisector of segment GE, okay? So that means if GF is 5, we're asked to find EG, then EG is also 5, okay? Now let's take a look at number 17. The directions tell us that point D is the circumcenter of triangle ABC. So let me just highlight, let's see, here's triangle ABC, okay, and point D is the circumcenter. Remember, the circumcenter of a triangle can be on the exterior, okay? Now, what was the definition of a circumcenter? A circumcenter is the point of concurrency of the 3 perpendicular bisectors of the segment. So here's one perpendicular bisector, here's the second perpendicular bisector, and then the third one is kind of squeezed in here. Okay, so the 3 perpendicular bisectors intersect at a point called the circumcenter. And remember, the circumcenter is the center of a circle that is circumscribed about the triangle, okay? And so when we say that D is equidistant from the 3 vertices, another way to think of that is that D is the center of this green circle, so that means that DA, DB, and DC are radii of that circle, and of course radii are always going to be congruent. So we can think of it in terms of radii of the circle, or in terms of our theorem that says the circumcenter of a circle is going to be equidistant from the vertices of the triangle. So what are the 2 segments that are congruent to AD? Well, that would be CD and BD. So CD and BD. Now let's take a look at number 21. We're asked to find AF. Okay, so what I want you to notice is that A lies on this ray, which is, the ray is the angle bisector of angle DEF. So we have a point that lies on the angle bisector of an angle. So we have a theorem that says whenever a point lies on the angle bisector of an angle, then it is equidistant from the sides. So if AD is 11, then AF is also 11. Conversely, let's look at number 22. Okay, here we see that this point D is 39 units from both sides of the angle, so that means D lies on the angle bisector. We're asked to find angle DBA, and since point D lies on the angle bisector, we know that if angle DBC is 17 degrees, then angle DBA is also 17 degrees. Okay, then let me give you a little bit of help on this section where we're told that point P is the incenter of triangle AEC. So if point P is an incenter, remember the definition of an incenter, that means that point P is the point of concurrency of the 3 angle bisectors. So let me just highlight those. Okay, so for example, in number 29, when you're asked to find angle DAC, well, remember, if this yellow segment is an angle bisector, then if angle DAE is 33 degrees, angle DAC will also be 33 degrees. Let's go back to number 27, where you're asked to find PB. Okay, so remember, PB is the distance from the incenter to a side of the triangle. Remember, the definition of the distance from a point to a line is the measure of the segment that's perpendicular. So what that means is this little triangle, let me highlight, here, let me shade it in blue. This little blue triangle is a right triangle. So when you're asked to find PB, okay, look at this blue triangle where you know two of the three sides. You know 13 is the hypotenuse, and you know one of the legs is 10.9. So use Pythagorean theorem. You'll probably need to use a calculator as well to find this other leg with Pythagorean theorem. Then remember, once you know what PB is, an incenter is equidistant from all three sides of the triangle. So in number 28, when you're asked to find DE, which is this segment, use this little right triangle. You'll know the hypotenuse. You'll know PD because it's going to be the same as whatever PB was, and then use Pythagorean theorem to find this missing side DE. Okay, so I hope those hints help you. If you have more questions about your homework, be sure and ask me in class, and I'll be glad to help you.